everyone. In this video I'm going to show you how to solve a Mealy machine and a Moore machine, a design problem of a Mealy machine and a Moore machine using an example that has two inputs and has two outputs. Okay, so the idea is to design this problem that I'm going to explain in a moment, to design it twice, okay, two times. The first time is using the Moore machine, and the second time is using the Mealy machine, the Mealy design procedure. Okay, so what does the problem ask you? It asks, it's given two bits as an input. Okay, so you have a system that takes two bits. The first one is called X, the second one is called Y. Okay, and gives us two outputs, Z1 and Z2. Okay. And what is required is, basically these X's and Y's, they are single bits, that's a single bit and that's a single bit, but they are received in sequence. So a single bit right now, and after one clock cycle, receive another bit from each one, and so on and so forth. Okay? And what is required is to design a machine that detects the sequence 001100. Okay? So what is required is that this machine, once it detects 00 followed by a 11, it outputs Z1 equals 1. Okay? So in that case, Z1 has to be 1. Okay? When it detects 00 followed by a 11. Right? And if in the third clock cycle it received a 00, it should output Z1 equals 1 as well. Okay? And Z2 equals 1. Otherwise, Z1 and Z2 are zeros. Okay? So let's have this example. Let's assume that in the first clock cycle we received 00, then we should output 0 at Z1 and 0 at Z2. If we received in the second clock cycle, we received 1 followed 1 and then a 1. 1 on the X and 1 on the Y. We should output 1 at Z1 and 0 at Z2. Because Z1 is defined as the output equals to 1 whenever we receive 00 followed by 1, 1. Okay? And then in the third clock cycle, we received a 0, 0. Okay? Which means that we should output 1 on Z1 and 1 on Z2. Alright? Then we received another 1, 1. Okay? So this is in fact a part of the sequence. Yes, the 00 was used before to output this 1, 1, but it is in fact a part of the sequence. And so in the last two clock cycles, I received 1, 1 and 0, 0. Okay? Which means that I should output here 1 and output here 0 to mimic this, to talk about these two ones. This 1, 0 represents that I have an output of Z1 equals 1 and output of Z2 equals 0 because I received in this time slot 1, 1 and in the previous time slot I received 0, 0. In the previous clock cycle I received a 0, 0. Okay? What if I receive 1, 0? Well, that is not a part of the sequence that I'm looking for, so that is 0, 0. Okay? 0, 0 again, that is 0, 0. Okay? 1, 1, that is 1, 0. Okay? So remember here, for this 0, 0, I know that the reason why I put a 0, 0 here is because I did not receive a 1. I did not receive the sequence that I'm looking for. Okay? The reason why I put here 0, 0 at the output when I received the 0, 0 is because I did not receive the sequence that I'm looking for. Although you might say, yeah, okay, but 0, 0, 1, 1, and then here we receive the 0, 0. So why don't we output a 1, 1? Well, because they're not contiguous. They have to be one followed the other. They have to be in sequence. They have to be contiguous. 0, 0 followed by 1, 1 followed by 0, 0. They have to be neighbors in time slots. Okay? So, output here, after receiving this 0, 0, so output 0, 0, receiving 1, 1 lets me output a 1, 0. Okay? Receiving 1, 0 means that I'll output 0, 0. Okay? 0, 1, then 0, 0. okay? And this time slot 0, 0 as well, okay? And perhaps if I receive 1, 1 here, then I output a 1 followed by 0, and then 0, 0, output 1 followed by 1, okay? So we want to design a system that performs like this, okay? So let's start first with the Moore machine. Okay? The Moore machine tells us that whenever you have a state, you have to put the output of the state inside the state. Okay? So what do I mean by that? Let's first start with the Moore machine. How do we design a Moore machine? We need to start with an initial state, okay, which is called, I'm going to call S0. And this S0 means that whenever the system is powered on, I start in this initial state. Okay? So it's an initial state. Whenever the system is powered on, the system powers on in this state. And of course, you expect that the output is going to be 0, 0. We have to include 2 bits in the output. Why? Because I have 2 outputs that are required to be coming out of the system. Okay? So, this, if I want to do a definition table, S0 represents initial state. Okay? And the output associated with this S0 is 0, 0. Okay? So remember, this is the output. Okay? Output Z1 and Z2. Okay? So, and then when I'm at this initial state, I expect to receive 2 bits, X and Y. Okay? And this is why I need to take all the possible combinations out of this X and Y. There are 2 bits, so I expect to see 2 to the n bits, to the n arrows. Okay, which is 2 to the 2, because I have 2 bits, so that's number of input bits, okay, so which is equal to 4 arrows out of each state. Okay, I have 4 arrows coming out of each state. Okay, the first arrow, the second arrow, the third arrow, and then the fourth. What is the first one? The first one is 0, 0. That is one of the possibilities. 0, 1. So x equals 0 and y equals 1. Or 1, 0, x equals 1, y equals 0, or 1, 1. I do not have any other possibility. Okay? Let's start with the 0, 0. So I need to ask myself, is this 0, 0 a part of the sequence that I'm looking for? It turns out to be, yes, 0, 0 is a part of the sequence that I'm looking for. So I need to retain this in the memory. So I need to create a new state. And I'm going to call it S1. What is the output in that case? What is the output associated with this state S1? The output should be 0, 0. Why? Because, yes, receiving a state, receiving an input of 0, 0 means that we should not yet output anything, neither on the Z1 nor on the Z2. Okay? Let's continue with 0, 1. Is 0, 1 one of the sequences that I'm looking for? Is it a part of the sequence that I'm looking for? It turns out to be not the case. And that's why I have to loop back to S0. Why? Because it means that I'm at an initial state. Still, I haven't yet received the output that I'm looking for. Okay? Similarly, the 0, 1, the 1, 0 loops back to itself again, loops back to state S0 as well. Why? Because 1, 0 is not a part of the sequence that I'm looking for. Okay? So, What about the 1, 1? 1, 1 is a part of the sequence that I'm looking for. Well, it is a part of the sequence that I'm looking for, but it is not the very first beginning of the part of the sequence. So even if I received a 1, 1 followed by a 0, 0, yes, it is a part of the sequence, but I should not output a 1, neither on the Z1 nor on the Z2. Why? Because it is not preceded with 0, 0. Remember, in initial state, I haven't received anything yet. I have the previous time slot, the previous clock cycle, has not received anything, any parts of the sequence yet. So that's why even the 1, 1, it is not, although it is a part of the sequence, but it is not the very beginning, the very first sequence that I'm looking for. So the 1, 1 has to go back to state S0. Okay? So right now I finished state S0. Do I have any other states? Yes, I do have another state, which was created, which is called S1. Let's have a look at S1 and see all of the possibilities that might come out of S1. Well, I definitely have 4 arrows, 4 possibilities, so I need to take them all into consideration. Okay? 0, 0, what happens? And 0, 1, 1, 0, and 1, 1. If I receive a 0, 0, is it a part of the sequence that I'm looking for? Well, right now, if I did receive a 0, 0, so far I have received 0 followed by a 0. Okay? Then this 0, 0 means that in the second time slot I have received a 0 followed by another 0. It is not a part of this whole sequence, is not a part of the sequence that I'm looking for. I need to receive 0, 0 followed by 1, 1. But I received 0, 0 followed by 0, 0. So this is not really what I'm looking for. Okay? So the question is, shall I reset back to state S0? Well, if I reset back to state S0 means that it is an initial state, which means that I haven't received any part of the sequence so far. But in fact, the last time slot, which is the one that is happening at the moment, is 0, 0. So it is a part of the sequence. So in case I received the 1, 1 in the following time slot and received a 0, 0 in the subsequent time slot, then in that case I should output a 1, 1. So if I return back to S0, so I'm going to mess up with the 0, 0 that I have received so far. So the best next state is to loop back to S1. Why? Because S1 is defined as last 2 bits are 0, 0. Last 2 bits are 0, 0. Okay? So, which means that that's why I had to loop back to state S1. Okay? So, what about the 0, 1? Well, definitely the 0, 1 has messed up with the 0, 0 that I have received so far. What do I mean by messed up? I mean that it does not benefit me anymore. Because if I receive a 1, 1 here, this 0, 0 won't be associated, is not a neighbor for the 1, 1. And that's why this 0, 1 will let me loop back to state S0. And that is the same thing as 1, 0 as well. Okay? What about 1, 1? Well, 1, 1 is a part of the sequence. Why is that? Because if I receive the 0, 0 followed by a 1, 1, then I'm looking at a part of the sequence that I'm looking for. Okay? Which means that I have to create another state, and I'm going to call it S2, and the output in that state, S2, is going to be 1, 0. Why 1? Because whenever I receive 0, 0 followed by 1, 1, I should output at Z1, I should output 1. And at Z2, I should output a 0. Okay? And that's why S2 is called the second state, which is defined as last 2 bits are 0, 0, 1, 1. Okay? 0, 0 followed by 1, 1. Okay? Alright. So, what about S2? Let's first finish S1. Have we finished S1? Yes, we did consider 0, 0. We considered 0, 1. We considered 1, 0 and 1, 1. Alright? So, let's have a look at S2. I could either receive 0, 0, or could receive 0, 1, or could receive 1, 0, or could receive 1, 1. Alright? So, 0, 0. Is it a part of the sequence that I'm looking for? Well, yes, 0, 0, 1, 1, and then 0, 0. So far, when I'm at S2, I have received 0, 0, followed by 1, 1. So receiving a 0, 0 here again means that I have received 0, 0, 1, 1, 0, 0. And that's why I need to go back to, another third state, which is called S3, which is the fourth state. And the output is 1, 1. Okay? So can I make use, instead of creating, because we know that creating new states is highly complicated. It's something very complicated. Complicates the design a lot. So the question is, can I make, with this 0, 0, receiving this 0, 0, can I make use of any of the previous states so that I can go to that previous state without the need to create another new state? Well, if I go to this initial state, let's see, well, in that case, the value of the output is going to be 0, 0. And even the concept of state S0 means that I have received an initial state. It's an initial state. I haven't received anything so far. So it is totally wrong to route this arrow back to the initial state. Okay? Because of two things. Because of the definition and because of the output. Okay? So let's have a look. Instead of creating this S3, we cannot go to S0. So let's study if we can go to S1. Can we go to S1? Well, the output is also 0, 0, which should not be the case. The output, when we receive a 0, 0, the output should be 1, 1, okay, in the third clock cycle. So that's why I cannot go back to state S1. So can I go back to state S2, loop back to state S2? Well, you cannot. Why? Because the output Z2 will not be a 0. Okay? And that's why creating a new state is mandatory for this arrow. Okay? What about 0, 1? Well, if I receive the 0, 1, then so far I would be receiving 0, 0, followed by 1, 1, followed by 0, 0. Okay? Is this total sequence a part of the sequence that I'm looking for? It is not. And that's why this has to go back to state S0. Okay? Has to go back to state S0. Alright? So, what about state? Let me route it here so that I can make room. Okay? So, 0, 1 will route back to state S0. Why? Because I cannot route it back to anything, any of these two states, not even S2. Why? Because so far S2 it represents received 0, 0, followed by 1, 1, followed by, 0, 0, followed by 1, 1. So if you route it back to 0, 0, although you have received 0, 1, okay, so right now, what if I'm studying this sequence, 0, 0, 1, 1, 0, 1. If I receive a 0, 1 at the third clock cycle, then this means that the last two are 1, 1 and 0, 0. That's the last two clock cycles. Which means that I cannot go back to state S2, because S2 represents last two clock cycles. I received 0, 0 followed by 1, 1. Okay? Which is not the case here. 1, 1 followed by 0, 1. Okay? So, 1, 1 and 0, 1 is not a part of the sequence that I'm looking for. Okay? So, let's look at 1, 0. Well, 1, 0 is the same as 0, 1. Okay? That's 1 and 0. Right? 1, 0 is the same. Okay? So I do not expect that 1, 0 would do any good to me. Okay? And that's why it will route back to the initial state. Okay? Routes back to the initial state. Alright. Let's have a look at 1, 1. Receiving 1, 1. What does 1, 1 represent? Represents that we have received 0, 0, followed by 1, 1, followed by 1, 1, which is not a part of the sequence that I'm looking for, and that is why 1, 1 is going to route back to state S0 again. Okay? So, what is the definition of S3? S3 means that we have received so far, last 3 cycles are 0, 0, followed by 1, 1, followed by 0, 0. Okay? What is the output associated with S1? S1 has an output of 0, 0. Output associated with S2, 1, 0. And that with S3 is 1, 1. Okay? So, are we done? This has 4 arrows. This has 4 arrows coming out of it. This has 4 arrows coming out of it. But this doesn't have any arrow coming out of it. So we need to take all of the possibilities. Because when you receive 0, 0, followed by 1, 1, followed by 0, 0, you do not expect that the system is going to stop. Still, you're going to receive in the 4th, 5th, and so on clock cycles, you're going to receive some other bits. So you need to take them into consideration. Okay? So, S3, shall I route it back to the initial state? Well, the problem is if you route it back to the initial state, then this is an indication that you do not want to retain the previous time slot value. What is the previous time slot value? When we are at S3, we have received so far 0, 0, followed by 1, 1, followed by 0, 0. Okay? So, these 3, when we receive 0, 0, followed by 1, 1, followed by 0, 0, we output 1, 1. However, we should not go to the initial state because the previous clock cycle is a 0, 0. But the initial state does not represent 0, 0. The initial state represents an initial state that we have not received anything so far. It's a reset state. Okay? And that's why you need to go to a state that represents 0, 0. Which one represents the 0, 0? S1. Okay? And that's why this goes to S1 if you have received 0, 0. Okay? So if I received a 0, 0, I was referring to basically this value. Okay? So again, I was discussing this arrow. Okay? This arrow means that I have received, after the 0, 0, I have received another 0, 0. Okay? Which means that this 0, 0 should not be routed to the initial state. Okay? Why? Because this 0, 0 is the last bit that I have received so far, while the initial state represents that I haven't received any part of the sequence in the last couple of time slots. But although I really have received, this 0, 0 is in fact a part of the sequence that I'm looking for. Okay? That I'm looking for again. Okay? Because I have already received, but I'm still, the machine is not going to stop. Okay? So that's why we need to route it back to S1. Okay? I need to route it back to S1. Alright? So, that is for 0, 0. We need also to take into consideration the 0, 1. 0, 1 case. Where does the 0, 1 case go? It needs to go back to the reset state. Why? Because 0, 1 is not a part. Okay. Similarly, whether it's a 0, 1 or a 1, 0, okay. In both cases, you go to state as 0, but you go to state as 0. But if it is a 1, 1, where do I go to if I receive the 1, 1? What is the sequence that I have received so far when I would state as 3? 0, 0, 0, 1, 1, 0, 0. Receiving 1, 1 means that there is a 1, 1 here. Okay? And this represents what? Represents that at the last 2 clock cycles, well, the last 3 clock cycles are not the sequence that I'm looking for. Okay? But the last 2 clock cycles are 0, 0 and 1, 1, which is something that I'm really looking for, which is S2, 0, 0, 1, 1. 0, 0, 1, 1. Okay? Because just in case I received a 0, 0 in the following clock cycle, I should output a 1, 1, which is the case with S2. And that's why 1, 1 needs to go to state S2. Okay? And this completes the state diagram. Why does this complete the state diagram? Because why does this complete the state diagram? Because this S3 has 4 arrows, 1, 2, 3, 4, and this S2 has 4 arrows as well coming out of it. S1 has 4 arrows coming out of it. S0 has 4 arrows coming out of it. Okay? So the key idea is that to know that your state diagram is done, once you count all of the arrows coming out of each state, and you find them equal to the n, where n is the number of input bits to the system. Okay? Remember, it's coming out of the state, not coming into the state. You do not care about the arrows that come into the state. You care about the arrows that come out of the state. Why? Because you need to take all of the possibilities in that state. All of the possibilities that could happen at that state. Okay? Right now, we are going to do, that's the Mealy machine, that's the moon machine, and we are going to do the state, we're going to do the state transition tape. Okay? Okay, so I have redrawn the state diagram again in a cleaner way. Why? Because it was a mess. Well, that's usually the case. Any state diagram at the beginning is a mess because you really need to work it out and redraw, and you do not know how it's going to look like. So after you finish writing down the state diagram, if you were not in an exam, if you had some time, I would redraw the state diagram in a cleaner way. Okay, so that's basically what I have done here. So how did I organize it? I organized it S0, S1, S2, S3. S0 is the initial state, initial reset state, where no parts of the sequence have been received so far. And that's why it represents, whenever I receive a 0, 1 or a 1, 0 or a 1, 1, I loop back to the same reset state. Okay, but if I receive a 0, 0, then I advance to a state S1 so that I retain this in memory. S1 means if the machine is at state S1, this means that the machine is retaining the value of 0, 0. Okay, still it is outputting a 0, 0, but it is different than this 0, 0 in the sense that this 0, 0 means that we have received something, a part of the sequence so far, but as this S0 represents that nothing have been received so far. Okay. Okay, so S1. If I receive a 0, 0 while I'm at state S1, this is an indication that it is a part of the sequence, but I cannot advance, okay, because so far this 0, 0 represents 0, 0 followed by a 0, 0. So it is not a part of the sequence that I'm looking for, okay, so that is the sequence that I'm looking for, okay, but it is not a part of the sequence, only a part of it is a part of the sequence, so this 0, 0 will be counted a part of the sequence, just in case I receive 1, 1 and 0, 0 after that, so I need to count all this, and that's why I loop back to state S1, okay? If I receive a 0, 1 or a 1, 0, I have to reset back, okay, as usual. Okay, 0, 1 and 1, 0 does not represent any part of the sequence, and that's why it resets, it messes up with our history, with everything that we have received so far. So 0, 0 followed by 0, 1 means that this 0, 0 is going to be cancelled, and the way that we show that it is cancelled on the state diagram is by looping back to the initial state, which represents that I haven't received anything so far. Okay, let's advance S1. What if I receive a 1, 1 while I'm at state S1? I go to state S2, because S2 is a 1, 0. It has an output of 1, 0. And S2 represents that I have received 0, 0 followed by a 1, 1 so far. Okay, so this is S1. Yeah, okay, so this S1 goes to state S2 if I receive an input of 1, 1. Okay, while I'm at state S2, whether I receive a 0, 1, 1, 0, or 1, 1, in all cases, 0, 0, 1, 1 represents state S2. Whether I receive a 0, 1, or if I receive a 1, 1, okay, or if I receive, so if I receive a 0, 1, or 1, 1, or 1, 0, in all three cases, this does not constitute any part of the sequence. And even the 1, 1, which constitutes a part of the sequence, I cannot I cannot build up over the 1, 1. And that is why this 1, 1 represents a reset. Nothing in the future is going to make use of this 1, 1. Okay? So, let's erase this. Okay, and erase this. And that's why I have to reset back. Let's proceed S2. If we have S2 and I receive an input of 0, 0, this means that I have received so far 0, 0, followed by 1, 1, followed by 0, 0. And that is why I have to output a 1, 1. Okay? So, what if I receive, if I'm at state S3 and I receive another 0, 0? So state S3 represents this part, which is 0, 0, followed by 1, 1, followed by 0, 0. What happens if I receive another 0, 0? Well, another 0, 0 represents the going back to state S1, because so far I have received S0, 0. Okay, so go back to state S1. And if I receive a 1, 1, then instead of this 0, 0, if I receive a 1, 1, so this constitutes a part of the sequence that I'm looking for. So that's why I go back to state S2. Okay, and again the 0, 1 messes up with everything and initializes us, resets the system back at state S2. Remember that these two rules, we're going to make use of them always in any of the, whether it's a Moore or a Mealy machine. Okay. The first one is that I'm going to talk about at the moment, which is the number of arrows out of each state is 2 to the n, where n is the number of inputs to the system. Here the system has two inputs, x and y. So that is the x and that is the y. Okay, x could be 0 or 1, y could be 0 or 1. So two possibilities to power the number of inputs. Make sure that each state has exactly 4 inputs in our case. This is 4 for our case. 2 power 2 is 4. So that's why each state has exactly 4 arrows. This represents 3 arrows plus 1. This 1, 2, 3, 4, and so on and so forth. Okay? So we've finished the state definition table. Do not forget to write down the output associated with each state in the state definition table of the Moore machine. That is only for the Moore machine. In the Mealy, we do not write down an output. There isn't any outputs associated with the Mealy machine, with the state of the Mealy machine. When it comes to the Mealy, we'll talk about this. Okay, after the state diagram and the state definition table, what do we do next? We need to do a state transition table. Why is that? This is a more organized way, other than this graphical way, to represent the how the system, how the machine operates. Okay. How do we do the state transition table? We write down a present state and an input, present state column, input column, okay, and we fill in this next state and the output based on this state transition diagram. Okay. So how did I organize this? The present state. I have, how many states do I have? I have 1, 2, 3, 4. 1, 2, 3, 4. Okay, but at each of these states, I have 4 possibilities of the inputs, which comes from this rule. 4 possibilities. And that's why I have to take into consideration the 0, 0, 0, 1, 1, 0, and 1, 1. And 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay? And that's why each row of these is going to represent an arrow from this diagram. Okay? So let's fill it in. I'm going to postpone the binary at the moment. I'm going to fill in the next state and the output. Usually, a lot of people write down the output of the Moore machine in the state transition diagram. I prefer that you do not do this, although it is possible. Both ways could work. But I'll teach you even an easier way so that you fill in, even if you fill in the output, you won't depend on this output to do the K-maps. And I'm going to talk about this in a moment. Let's fill in first the next state. In the Moore machine, when you fill in the state transition table, you fill in first the present state and the input. You fill them the way that I've done it at the moment. Okay, states and then inputs. Okay, associated with each state 4 inputs. And then fill in the next state. And after that, by the end of the day, you fill in the output. Okay? So let's fill in the next state first. Do not fill in the output while filling in the next state. Fill in the next state first. S0. I have an input of 0, 0. What is the next state? S0, an input of 0, 0, means that we go to state S1. So write down here S1. Okay? Remember that I do not write the output. Yes, S1 has an output of 0, 0, but I'm not going to write down the 0, 0 here. Okay, I'm filling in the next state first. Okay? S0, you have an input of 0, 1. Input of 0, 1. You go back to state S0. So I go back to state S0. 1, 0, you go back to state S1. So S0 has an input of 1, 0, you go back to state S0. Similarly, S0 has an input of 1, 1, you go back to state S0. Let's proceed to S1. S1, you have an input of 0, 0, 0, 1, 1, 0, 1, 1. Okay, so 0, 0 is S1. Okay, and then what do you have else? 0, 1 and 1, 0. 0, 1 and 1, 0 both are S0. Okay, and 1, 1 goes to state S2. Okay, let's move on to state S2. S2 has an input of 0, 0. It goes to state S3. Okay, 0, 1 goes to state, so all of these 3 go to state S0. So S0, S0, S0. Okay, and at state S3 we have an input of 0, 0 goes back to state S1, and these 2 goes to state S0, goes to state S1, and these 2 go to state S0, and then 1, 1 goes to state S2. 1, 1 goes to state S2. Alright? Fill in the next state, and then fill in the output. How do you fill in the output? You do not look at the state diagram. Okay? You look in the Moore machine, when you fill in the output, you look at the state definition table. What is the present state? The present state is S0. And in that case, the output associated with this present state is 0, 0. Okay? So you write down here 0, 0, 0, 0, 0, 0, 0, 0. So this 0, 0 does not come from S1. It comes from the present state. Again, I repeat. This column of the Moore machine, the output here is filled in based on the present state, not on the next state. Okay? And this is a very important part in the Moore machine that a lot of people do make a mistake in. Do not fill in the output based on the next state. Fill it in based on the present state. And that's why you need to make use of the state definition table. Okay? S1 has 0, 0. Okay, so that's S1. S2 has an output of 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, S3 has an output of 1, 1. Okay, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so as you can see, there is some sort of redundancy in the information, but still, this is the way that the Moore machine is filled. Anyways, I'll teach you even an easier way to build the K-maps without looking at this column. Okay, but let's proceed. Okay, Are we done with the state transition table? In terms of this diagram, yes, we're done. But in terms of the state transition table itself, we still need to fill in these binaries. Okay? So, since we have here 4 states, then what I'm going to do is that I'm going to assign a binary sequence for each state. How many bits do I need to assign for each state? The number of state variables, the number of bits, okay, so that's basically number of bits. When I say state variables, it equals number of bits that are to be assigned for each state equals the logarithm to the base 2 of the number of states. Okay, and here this is 4. Log to the base 2 is equal to 2. Okay, and what am I doing here? So let's assume that you got a number 2.3. This number, perhaps you might in another example you might have log to the base 2 to the number 5. So in that case, log to the base 2 to 5 is not equal to 2. Okay, it is equal to, okay, it is equal to 2 point something. Okay, so in that case, you need to round it up. 2.3 or 2.1 or 2.2, whatever. Okay, so you need to 2.3, yeah, or a little bit less. So you need to round it up, okay, which means that it is equal to 3. You have to assign 3 bits. But in our case, it is already rounded to a whole number. And that is why we do not make use of this rounding up in this particular example. But in another example, you might need this rounding up. You need to approximate it to the smallest higher integer. Okay? So, in our case, it is 2 bits. Okay? So I'm going to assign here 0, 0, 0, 1, 1, 0, 1, 1. It's arbitrary. Okay? The convention is to assign S0, assign it binary 0, 0, S1, assign it 0, 1, 1, 0, and 1, 1. If it's 3 bits, then you assign 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on and so forth. Okay? So, right now we have, that is the binary assignment. Binary assignment. So I write here binary. Binary. Okay? These are the binary assignments. These are not the outputs. These are the binary assignments. And what I'm going to do here is that I'm going to look at the S0 and I'm going to write its binary assignment here. So here S0 is 0, 0, 0, 0, 0, 0, 0, 0. Okay, S1 is 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay? Similarly, I'm going to do the same thing for the next state. S1 is defined as 0, 1. S0, 0, 0. 0, 0, 0, 0. Okay? S1 is 0, 1. 0, 0, 0, 0. 1, 0, 1, 1. 0, 0, 0, 0, 0, 0. 1, 0, 1. That's a 0, 0. 0, 0. No, this is a 0, 1. Okay, and this is a 1, 0. Okay. Okay, so here I'm going to write down Q1, Q0. And here I'm going to write down Q1 plus, Q0 plus. So this represents the flip-flop that has the most significant bit, and this represents the flip-flop that has the least significant bit. Okay, and that's the next state of this flip-flop. Okay, so what I'm going to do at the moment, I'm going to write down, I'm going to implement this machine using D flip-flops, okay, because it's much easier to understand, and that's why I do not need to append columns here. This becomes the D values, okay, so these are the D values. This is D1 and this is D0. This column becomes D1 and this column becomes D0. Why? Because D1, because Q1 plus equals D1 and Q0 plus is equal to D0. Okay? So there is no need for us to append 2 columns as if it was a JK flip-flop or an SR flip-flop or a T flip-flop. We're going to do the easier part here and choose the D flip-flop. Okay? So, D flip-flop. what do I need to do in order to implement using the flip-flops? What I need to do is that I need to implement some K-maps, because these K-maps are going to give me the equations associated with the equations that I'm going to use to build the circuit. Okay, so we're going to do right now K-maps, and the K-maps are going to give us some equations, and these equations are going to give us the circuit that implements the machine that solves this problem. Okay, so before I do the K-maps, I need to know how many K-maps am I going to do. Number of K-maps, okay, let's write down a rule here. Number of K-maps in the Moore machine and in the Mealy machine as well, okay, equals number of bits, number of flip-flops, plus number of outputs of the system. Okay, how many flip-flops do we have for our case? That's a rule. All these rules are for the Mealy and the Moore. Okay, number of flip-flops, we have 2 flip-flops, and number of outputs, we have 2 outputs. Okay, so we're going to start with the flip-flops and then proceed with the K-maps of the outputs. Okay, let's erase this. We do not need this information anymore. We already have the information in the state transition table. Okay. Okay. So after drawing the K-maps, we have drawn 2 K-maps for the flip-flops. Okay, flip-flop inputs D1 and D0, and we have drawn 2 K-maps for the outputs Z1 and Z2. Number of K-maps equals number of flip-flops plus number of outputs. Okay, so why did I write down the K-map as a 4-variable K-map? Because the number of variables in the K-map of the flip-flops, okay, when we talk about the flip-flops, whether it's a Moore machine or whether it's a Mealy machine, then in that case the number of variables in the K-maps equals the number of flip-flops plus the number of inputs. How many flip-flops do we have? We have 1 flip-flop, 2 flip-flops, okay, so we have 2 flip-flops and 2 inputs, and that's why it is 4 in our case. Okay, so this number of variables is 4. Okay, so that's why it is a 4-variable K-map. How do we write down a 4-variable K-map? Using a 4x4 matrix. Okay. How do I fill in? And that is the case for the 2 flip-flops. This one and that one, D1 and D0. And I'm going to talk about the output K-maps in a moment. For the K-maps, how do we fill in the K-maps? The easiest way that I recommend is that you number these cells of this K-map according to these numbers. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, there's something missing. 0, 1, 2, 3. Okay, 4, 5, 6, all the way through 15. Okay? All the way through 15. Okay? And you fill them in. So you fill them column-wise or row-wise? Column-wise or row-wise? Well, we fill them in, let's see. Okay. So, give 0, 1, 2, 3 is S0, 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 which means 0, 0, 0, 0, 0, 0, 0, 0. So the binary are constant. The Q1 and Q0 are constant. We have Q1 and Q0 are 0, 0, 0, 1, 1, 1, 1, 0. So this column represents 0, 0 for Q1, Q0. But this row represents a constant value for X and Y, okay? Which is not the case. We want 0, 1, 2, 3 to be constant across 0. So that's why I write down here 0, 1, 2, 0, 1, 2, and 3. Okay? And that's what 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? Because remember that this is a gray code 0, 0, 0, 1, 1, 1, 1, 0. Okay, so 0, 1, 2, 3. Okay? The same goes for this K-map. Alright, let's fill in the K-map. look at this column, okay, which is the column of Q1, because we're filling in the K-map for D1. So what is the column for the Q1? So that is, oh, we need to look at the next state, not the present state. The next state is 0, 0, 0, 0. Okay? So 0, 0, 0, 0. Okay? And then 0, 0, 0, 1. 0, 0, 0, oops. 0, 0, 0, 1. Okay? 0, 0, 0, 1. Right? And then 1, 0, 0, 0. 1, 0, 0. Oops, I should fill it in here. 1, 0, 0, 0. Right? And then 0, 0, 0, 1. 0, 0, 0, 1. Right? So this becomes the K-map. Usually people do not look at, put in these zeros, they fill in only the ones, and that's what I prefer. But if you're at the beginning of your study, you want to fill in the K-map using the zeros as well, that is fine as well. Here I'm going to fill in the K-map using the ones only. So I have a 1 at the 0 position and the 1 at the 4th position. Okay, so 1 at the 0 and 1 at the 4th position. Okay, and then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. One at the 4th position, 1 at 8, and 1 at 12. Right? 1 at 8, and 1 at 12. Where's 12? This is 12. Okay, and that's it. Okay, the rest are zeros. Okay, so let's write down the equation. How do we do the K-map for this one? We can circle these and then circle this one. So this becomes the Q0 is constant, Q0 is constant, and XY are constants. And they're ones. Plus Q1, Q0 bar, Q1, Q0 bar, and then XY, XY, right? For the D0, alright, so we have X bar, Y bar, right? So let's have a look at, right? Yeah, let's have a look at the output K-map. The output K-map, actually, it turns out that for the Moore machine, it is different than the Mealy machine, and that's why I wrote it down in green here. Okay? For the Moore machine, the number of variables in the K-map is equal to the number of flip-flops. Okay? How many flip-flops do we have? We have 2 flip-flops. Okay? So we're going to fill in the output variable K-map. Okay? But what I'm going to do is that I'm not going to fill in the K-map using these columns. I'm going to fill in the K-map using the state definition table. That's much easier, okay? And that's why it's better to write down the output using the to have a look at. It's much better to have a look at the state definition table than to write down the output from the transition table. Okay? So when this is okay, so that's the Z1 and that's the Z2. Let's look at the Z1. It is 0 when there are zeros. Okay, when is it 1? It is 1 when we have 1 0 or we have a 1 1. Okay, so this is Q1 and this is Q0. Q1, Q0, Q1, Q0, Q1, Q0. Okay, when do we have a 1 for? We're filling in this Z1. We have a 1 when we have S1 when we have a 1 0 or a 1 1. Where is 1 0? This is 1, okay, and 0, alright, 1 0, okay, and 1 1, which is this one, okay. So you circle it this way, okay. And we have a 1 only when we have 1, 1 for the Z2. Right? For the Z2, this is 1. Okay, so we have 1, 1. Okay? So let's write down this. It becomes equal to Q1, and this becomes equal to Q1, Q0. Right? And this becomes the equations that we need. Equation number 1, equation number 2, equation number 3, and equation number 4. Okay, write down. Right now I'm going to erase everything except the equations. I do not need anything except the equations at the moment. Okay? Okay. So after I erased everything, I rewrote down the equations again. And remember, there was a typo in one of the equations, which is the equation of D1. It read x, y, although it's supposed to be x bar, y bar. So please make note of that. The correct equation is x bar, y bar, okay, because it was in the first row. And D0, Z1, and Z2. That's all what I need. Okay. So how do we draw the circuit? We first draw the number of flip-flops. How many flip-flops do we have? We have 2 flip-flops. So we draw 2 flip-flops. And one of them is one I'm going to call Q1, and this is Q1, Q1, and this is D1, Q1, and Q1 bar. D0, Q0, and Q0 bar. Okay? Doesn't matter which one you put on the top, whether Q1 or Q2. Whether you put this here or put this here. Okay? But what's more important is that Q1 is on the top and Q1 bar is on the bottom. Q1 is on the top, Q0 is on the top, Q0 bar is on the bottom. Draw the clocks, okay, and connect them together. It's a synchronous machine, right? All the clocks are connected together. And then let's do the D1. What is the input for D1? D1 is Q0 multiplied by, it's an ORing between 2 terms. So I need to write down an OR gate. Okay? Has 2 inputs. Alright? The first one is called Q0 XY, so it's an AND gate between 3 terms. Okay? And the second one is an AND gate between 4 terms. Okay? The first one is an AND gate between Q0, X and Y. Q0, X and Y. And remember that this Q0 is not a switch. It is this Q0. But instead of messing up and do a huge mess with wires jumping all over the circuit, I prefer that you write it down as Q0. And it is implicitly understood that this Q0 is connected to that Q0. Okay? And the second one is Q1, Q0 bar, X bar, Y bar. Q1, Q0 bar, X, Y. This is X bar and Y bar. Alright? This is X bar and Y bar. Alright? Similarly, we have D0 is equal to ANDing between 2 things. Okay? Okay, what's the first one? It's X bar. The second one is Y bar. Alright? And the Z1 is Q1. Okay, so this is Z1. And Z2 is ANDing between 2 things, Q1 and Q0. Okay, that is ANDing between 2 things, Q1 and Q0. Z2. Right? At the end, if you would like to connect this to that, this is okay. If not, that's fine as well. So this is Q0 bar. Okay, and this is Q. Okay. Okay, and X and Y are the input switches. Alright, so if you want to try this machine, so you write down, like for example on Logisim or any Logicworks or whatever circuit, digital circuit software that you want to try this circuit on, bring 2 flip-flops, connect the AND gates, connect the OR gates, and put 2 switches. One of them is X and the other one is Y. And this X is to be connect it to a NOT gate to get the X bar and the Y as well. Y bar. I prefer that you write down these definitions so that you know that this X and Y are not different from the X bar and Y bar, so they are not separate switches. It's a single switch that controls X and X bar, but the difference is that there is a NOT gate. So do not connect this to a separate switches. It's not 4 inputs, it's just 2 inputs. One of them is the opposite of the other. Okay, each 2 is the opposite of the other 2. Alright, so this is the circuit for the Moore machine, and write down, as you can see, that there is no relation between Z2 and the inputs, between Z1 and the inputs. Z1 is only a function in the Q, it's function in the state only. Z2 as well, it's function in the state only, it is not a function in the inputs, and that is why it is called a Moore machine. Okay? So, right now we're going to do the Mealy machine. Alright? Okay, so to the Mealy machine. As usual, the Mealy machine has a reset state. Okay? We start with this initial reset state where we assume that no sequence have been received so far. Right? Again, we need to take into consideration all the possibilities, and I'm going to write down 0, 1 and 1, 0, okay, in the same arrow. Okay? So that's 0, 0, 0, 1, 1, 0 and 1, 1. Okay? As usual, as you expect, what are we looking for? We're looking for the sequence 0, 0, followed by 1, 1, followed by 0, 0. That's what we're looking for. If you receive a 0, 0, then you expect that this is going to be a part of the sequence, and that's why you need to continue to 0, 0. But you need to write down what the output is. We expect 2 outputs in the system, Z1 and Z2. Do we output anything at the moment? We do not, and that's why the output has to be 0, 0. Why did I mention the output associated with the arrow? Because in the Mealy machine the output is not in the state. Do not write anything except the state name here. Do not write any outputs. There is no outputs associated with the state, and that's why whenever I define the state, I did not say, yeah, the Z1 and Z2 is equal to 0, 0. I did not even write down what the inputs are. The state has nothing to do with the inputs and has nothing to do with the outputs in the Mealy machine. In the Moore machine, the state has to do with the outputs but has nothing to do with the inputs. Okay? So, here I do not write down the outputs. Okay? 0, 0, I get an output of 0, 0. 1, 1, I get an output of 0, 0 as well, because it's not a part of the sequence, and I loop back, okay? And the same goes for 0, 1 and 1, 0, okay? So you might want to write down them all on the same arrow, okay? So, whether it's 0, 0, 0, whether it's 0, 1, 1, 0, or 1, 1, all of them have an output of 0, 0. Okay? And please write down the output not as a dash. It has to be a slash. Okay? It has to be a slash, a forward slash. Alright? That is the convention worldwide. We have to follow it. Okay? So let's proceed. When we have an output, when we have an input of 0, 0, we said we need to go to a state S1, and this state S1 represents that we know that we have received a 0, 0 so far. Okay? So that's state S1. Again, I need to take into consideration 0, 1 and 0, 0 and 1, 0 and 1, 1. Right? And mention what the output is associated with each one of them. So that I do not forget, I'm going to write the backslash here. Okay, when we receive an input of 0, 0, what do you expect? I expect to go back to the same state because previously S1 is defined as receiving an input of 0, 0 so far. Right? So, S0 means that we're going to loop back to state S0 and output a 0, 0. Why a 0, 0? Because nothing needs to be outputted so far. Nothing, the sequence has not been received. Okay. What about 0, 1, and 1, 0? 0, 1, and 1, 0 are going to mess up with the 0, 0 that has been received, and that's why they need to loop back to that state. So whether it's a 0, 0, whether it's a 0, 1 or a 1, 0, the output is 0, 0. Okay? And the next state is S0. Alright? So, what if we receive 1, 1? The 1, 1 basically is a part of the sequence. Why? Because I have received 0, 0 so far, because I'm in state S1, and I received at the current clock cycle, I received the 1, 1. And this 1, 1 represents that it is a part of the sequence. Okay? So, I need to advance, okay, to the next state. Right? 1, 1, and output a 1, 0. Why output a 1, 0? Because when we receive a 1, 1, we need Z1 to be 1 and Z2 to be 0. And this is S2. Okay? S2 is the state that represents receiving 0, 0 followed by 1, 1 so far. You can see that it's kind of pretty similar to the Moore machine, although there might be some differences. Let's continue to see if there are any differences. Alright? Again, we need to consider what happens if I receive a 0, 0, 0, 1, 1, 0, and 1, 1. Okay? And I'm going to put this slash so that I do not forget to write down the output. Output has to be mentioned on the arrow. When I receive a 0, 0, then I definitely guarantee that this is a part of the sequence, because I received 0, 0, 1, 1, and then a 0, 0 so far. Alright? But what's really good about the Mealy machine is that this 0, 0, you do not have to go to another state. Alright? So the question that you have to ask yourself when you build a state diagram, you're asking yourself what the next state should be. What should the next state be? Alright? Always ask yourself this question. Do I need to create a new state, or can I make use of the previous states so that I do not have to create a new state? Because as you can see, as the number of states increases, the number of flip-flops needed increases. Okay? And that's why you try as much as possible to make use of the previous states. Okay? So, if I receive a 0, 0, this 0, 0 means that the sequence has been terminated, and I need to output a 1, 1. So yes, I know that the output should be a 1, 1. Okay? 0, 0, the output is 1, 1. But why do I need to create a new state? S3. Previously, in the Moore machine, I had to create a new state because I had to output a 1, 1. But right now, I'm outputting already a 1, 1 on the arrow. Regardless, you do not know how am I going to implement this, but you know for sure that the output is going to be associated with the arrow. It does not have to be associated with the state. So even if I go back to state S1, what is state S1? S1 represents receiving 0, 0 so far. Alright? So this 0, 0 is a part of, so let's assume that we receive 1, 1 and then a 0, 0 after that. So this 0, 0 is going to be a part of the next subsequent sequences, right? So why do I need to create, so I can make use of it in the next sequences. And the way to notate on the state diagram that I'm going to make use of this 0, 0 is by saying that this arrow should be routed to state S1. The only problem back in the Moore machine that did not allow me to do this is because S1 had an output of 0, 0. And I know that the 0, 0, this 0, 0 should have an output of 1, 1. And that is why I was not able to route it back, and I had to create a new state. And this new state had to be 1, 1. But in this Moore machine, in this Mealy machine, we do not have to do that. The output is already mentioned on the arrow. Okay? So, the 0, 0 that routes to S1 has an output of 0, 0. And this 0, 0 that is routing to S1 has an output of 1, 1. There is no conflict about this. There is no contradiction. Why? Because this arrow is totally different than this arrow. And the state is the same because the state represents that I have received a 0, 0 so far. You do not know how this is going to be implemented on the hardware, on the circuit, in a circuit, but this is the procedure that we can make use of in the Mealy machine. All right? And later on we'll see how we're going to implement this in on a circuit. All right? So we're done with the 0, 0. Let's look at 0, 1. What is 0, 1? 0, 1 means that we should reset back. Okay. 0, 1 or 1, 0. And the output should be 0, 0. Similarly, 1, 1 is a reset again, so I'm going to include it even here. Alright? Alright, so are we done? Well, let's double check. Each state has to have 4 arrows. 2 power 2 is 4, so each state has to have 4. This is 3 and 4. S1 has 1, 2, 3, and 4. Okay, and that's an arrow coming in. Alright? S2 has 1, 2, 3, 4. So we're done. So we did not need another state. The Mealy machine has S0, S1, S2, and does not have any S3. And that is why in the state transition table, that is why in the state definition table, S3 don't care. I don't care what the value of the state is. Okay, I'm not going to use it. Not used. Okay, not used. Alright, so back to the assignments. Alright, we want to assign a binary to each state. Again, I'm going to follow the convention. Okay, 0, 0 associated with S0, 0, 1, 1, 0, 1, 1. This is not assigned a don't care. It is a state, but it is not used, and that's why I prefer that you do not define it as don't care. You define it as not used, but it has an assignment. We will not use this state, but it is assigned a value. Okay? So, what we're going to do next, after the state diagram, we need to fill in this information in the state transition table. As usual, we're going to fill it in row by row. Each row corresponds to an arrow in the state transition table. And this is the state transition table for the Mealy machine. Okay? The first row represents S0. When I receive an input of 0, 0, I have a next state of S1. So I write down S1. But in the Mealy machine, I have to write down the output as well, because each arrow has an output associated with the state. Each arrow has an output associated with it. So that's why I have to write down the output as well. And the output associated with this arrow is 0, 0. So I write down here 0, 0. Okay? So I do not fill in this from the state definition table as it was the case in the Moore machine. Alright? State S0, I receive an input of 0, 1 or 1, 0. So 0, 1 or 1, 0 or 1, 1, all of them are having a next state of S0, 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 right? And the output is still 0, 0. Okay? State S1, what's the value of the input? The value of the input is S1, the value of the input is 0, 0, right? And the output is 0, 0. And it loops back to state S1. S1 and 0, 0. Okay? S1 and have an input of 0, 1. S1 and I have an input of 0, 1. Whether it's a 0, 1 or a 1, 0, it has the next state of S0. So S0 and the output is 0, 0. Okay, so now I filled in the rest of the table. These parts I filled them in. You pretty much look at this diagram and fill them in. What about the S3? The S3 is not used, and that's why its next state is a don't care, and the output is don't cares. I do not care what the output is because I guarantee that the next state, that this S3 is not going to be used. Okay, and that's why the binary assignment is going to be I don't care. Alright? Okay, let's fill in this column. Alright, after filling in this column, you're done with the state transition table. Right now, we want to fill in the state transition, we want to convert the state transition table into a circuit, and the way to do that is to fill in this, use this information and fill in some K-maps, and the K-maps that we're going to use, they're going to give us some equations, and the equations are going to give us a transition, are going to give us a circuit. Okay, let's go to the state, to the K-maps. Okay, so these are the K-maps. How many K-maps do we have? We have 4 K-maps. 2 for the flip-flops. We have 2 flip-flops, right? And 2 for the outputs, because we have 2 outputs. Why do we have 2 flip-flops? We have 2 outputs because we have, the system is asking us, the problem is asking us for 2 outputs. But why do we have 2 flip-flops? Because we have 2 bits for binary assignment, because we have at most 4 states. Okay, we have exactly 3 states. You take log to the base 2 to 3, you get a number smaller than 2. Alright. Number of variables in the K-maps. Number of variables in this K-map equals to the number of flip-flops plus the number of inputs. 2 flip-flops and 2 inputs, so it becomes a 4-variable K-map, and that's the same for the D0 as well. Let's write down the D0. The D0 is equal to, okay, 1 at the 0th row, and 1 at the 4th, and 1 at the 8th. 1 at the 0, 1 at the 4th, and 1 at the 8th. And the rest are zeros except the last 4 are don't cares. Except the last 4 are don't cares. Okay? So, you can fill in this table as well. You find that for the D1 you have only 1 at the 7th position, and you can fill in the same. For the K-map of the Mealy machine, of the output of the Mealy machine, why is it a 4-variable K-map? Because the rule is not the same one as the Moore machine. In the Mealy machine, the number of variables in the K-maps of the outputs equals the number of flip-flops plus the number of inputs. Alright? And that is the same for any Mealy machine. So the dimension of the K-map of the Mealy, of the output of the Mealy, is the same as that for the state of the Mealy. Okay? So that's dimension 4, and this is 4 as well. Alright, so the output, you can fill it in as well. You find that you have only 1, 1 for Z1, which is at the 7th position, at the 8th position, alright? And 1 at, yes, so that's the 7, okay? And for the 8th, you have 1 at the 8th for the Z2, right, which is this one. And the last column is don't cares. Let's do the K-map. Okay, so that's 1, which means that it is Q0 X Y. D0 is Q and X bar Y bar, right? And for this one it is Q1 X bar Y bar. For Z1 it is Q1 X bar Y bar plus Q0 X Y, right? And these are the equations that we need. Okay, what I'm going to do at the moment is that I'm going to write down the circuit using draw the circuit using these equations, and I do not need anything else other than these equations, right? Okay, so these are the equations, right? And I'm going to implement them on the circuit. I have two flip-flops because I have two state variables, and each of those flip-flops clock is connected to a master clock switch, right? And then I have the D1 on top, the D0 is in the bottom. D1 is Q0 multiplied by XY. So I have a big AND gate, has three inputs, Q0, X, and Y. The D0 is X bar, Y bar, X bar, and that's Y bar, right? What about the Z1? Z1 is the output, and it is an O-ring between two terms. The first one, that is Z1, okay? It's an O-ring between two terms. The first one is Q1 X bar Y bar, Q1 X bar Y bar, so that's Q1. Okay, so that's Q1, so I'm going to connect it directly, and that is X bar Y bar, okay, X bar Y bar. And the second one is Q0 XY, XY, okay. Similarly for Z2, it is a single AND gate, X bar Y bar, okay, Q0 and X bar Y bar, so that's Q1. Where is Q1? This is Q1, right, and X bar Y bar. This is X bar, and this is Y bar, and this becomes Z2, right? So that becomes the circuit. And one final note that I need to let you guys know: if you are going to implement this on a software, Logisim, or even on a hardware, whatever that hardware is, whatever the Logisim is, whatever the software is, please use a synchronization flip-flop. As you can see, the Z1 and the Z2, each one of them is a function in the input. It's not a function in the state alone. It's a function in the input, which means that if you change the input, the Z1 is going to change immediately, and it is not going to be synchronized to the clock. You won't need to wait for the clock for the input to change, okay? So you'll not be able to test it. You'll find yourself that, yeah, this is not working, but it's not really the case. It is working, but in order for you to see it working, you need to connect a synchronization flip-flop for each output. So that's a D flip-flop, okay, and it is connected to the input Z, and its output is Z1, right? The same goes for this. That's the clock, okay, and this not Z2, that's a Z flip-flop as well. This is the Q, and this becomes Z2. So the Z2 is the output of the flip-flop. Z1 is the output of the flip-flop. These have nothing to do with these flip-flops. These are additional flip-flops which are called the synchronization flip-flops, and that's why the synchronization flip-flops, in order for you to see, the reason why we need them is because so that you can observe it working, okay? If you do not put them, you need some sort of experience to see them working. Not everybody knows how to operate a Mealy machine, okay? So remember that these clocks are connected to this master clock. So ideally they're all connected together, right? So they are not separate clocks, right? So this is the Mealy machine, and I hope you guys have grasped the kind of the systematic procedure for this Mealy machine. The main aim was to provide you of an example of a Mealy machine and a Moore machine that has multiple inputs, not just one input. You have two inputs, which are the X and Y, and not just a single output, but also you have two outputs, and which becomes kind of more challenging, but still the same procedure of a single input machine works pretty much the same, and as you can see, it is all systematic, right? If you have any questions, please let me know, and I hope you guys have enjoyed this, and let me know if you have any problems that need to be explained. Right, see you later.